So hi, I'm going to talk about security of the JPEG protocol. This is a joint work with Michel Abdallah and Philip Mackenzie. So the JPEG protocol is a PAKE protocol. So a PAKE protocol is a password authenticated key exchange protocol. So basically, it enables two users, Alice and Bob, who only share a common low entropy password or even a 4-digit PIN number. So it enables them to generate a common secret key which is cryptographically secure. So obviously, with such a protocol, an adversary, Eve, can always try to guess the password used by Bob and then impersonate Bob and run the protocol honestly using the guessed password. So if she did not guess correctly, she won't get the same key as Alice and she won't get authenticated. But after several trials, she may end up finding the correct password, since there is only a small number of possible passwords, and she will get authenticated to Alice and get the same key as Alice. So this attack is called an online dictionary attack. And basically what we want is that this attack is the most powerful attack possible. And in particular, it should be impossible for Eve to look at a transcript between Alice and Bob and to check whether this transcript corresponds to a given password. Because if that's the case, she can just run her computer and find out which password were used by Alice and Bob, and that's terrible. Okay, so why should we use PAKE? So the first application is to replace the classical way of sending plain password over TLS for authentication. So why sending plain password over TLS is maybe not a good idea? Because if you do any typo in the URL, or if you click on a phishing link on some email, you may end up on the wrong website. For example, this website with just one letter difference with the real website. And then you will just send to this malicious website your password in plain text. So that's the worst that can happen. Why? If you used a PAKE protocol, the malicious website would have to guess correctly the password you want to use to be able to be authenticated or to be able to talk with you. And it's very improbable that the malicious website gets the password directly. And so you will end up with a fake connection, and you will look carefully at the URL and say, oh, that was not the good URL. So password authenticated key exchange are an additional layer of security on top of TLS. At least should be, because it's not used in practice. So a second application is to connect smart devices to smartphones. So let's suppose that you have a new smart devices and you want to connect it to your generic application on your smartphone. You don't want to type a big cryptographically secure key to connect to this device, because that's just too painful. You just want to type a 4-digit PIN number, for example. And PAKE makes this possible, and that's actually used in the new thread mesh network protocol standard for the Internet of Things. For example, so it's used in the Nest devices. Okay, so now what's JPEG? JPEG is a PAKE introduced by Howe and Ryan in 2008. So it's a novel construction which seems to avoid patents. So the construction is over a cyclic group G. So think an elliptic curve, or if you don't know elliptic curve, a multiplicative subgroup of ZQ. And it's based on a juggling technique, so hence the name JPEG. It's practical, it has been implemented and used, but up to now there was no security proof with a formal model. There was only some intuition in the original paper, but really no formal model. So at that point, the question is JPEG really practical? Should I use it? Okay, and if we compare JPEG with previous PAKE protocol, we see that the communication complexity of JPEG is 6 times worse than some idealized protocol, and it's also worse than standard model protocols that has this one. And concerning computational complexity, it's also worse than previous protocol. I mean, and it's even also 6 times worse than ideal model protocol. Okay, so why should we care about PAKE? Given that it's not more efficient than previous PAKE protocol. Okay, the point is PAKE seems to avoid patents, and JPEG, sorry, seems to avoid patents, and other PAKEs, with other PAKEs, the situation with patent is very unclear. So for business or for companies, JPEG is really kind of the only choice for PAKE, and it's used in practice. And in addition, if you like security, you will see that labels, so this bit string used to tie flows together, so these labels impact security, and if you choose them not very carefully, you may end up with an insecure protocol. And that you can only see it if you try to do a detailed security proof. And if you are more interested in crypto like me, you will see that Schnorr proofs are much more secure than they seem to be if you consider a slightly weak model of algebraic adversary, but this is still a reasonable model in practice. And you will also see an interesting proof of PAKE protocol, but only in the paper. Okay, so back main security result. So we show that the JPEG protocol, as proposed in the original paper, is secure under the DSDS assumption, which is a classical assumption, and assuming that the proof system used in the protocol is simulation extractable. And then we show that the proof system used in the protocol, which are Schnorr proof, are actually simulation extractable with some restriction, but that's okay in practice. Okay, so let's go into the details. So JPEG is a symmetric protocol between a client A and a server B. So the client pick 2 random scalar x1, x2. Here, compute these group elements, g to the x1, g to the x2, where g is some generator of the cyclic group. He sends everything to the client with a proof, to the server with a proof that he did that correctly. The server does the same. Then the client computes this group element from what he received from the server, compute a proof that he did that correctly, send everything to the server does the same, and at the end, the client checks the proof of the server. So sorry, I forgot to say, he also checks the proof of the server here, and he computes this key. So, okay, that's what the server does. And first, if you look carefully, you can see that both the client and the server, if they are honest and use the same password, they get the same secret key at the end. So, okay, so that's the correctness of the PAKE. But more interestingly, let's look at intuitively why this PAKE is secure. So that was explained in the original paper. So first, we suppose that Alice, or the client is honest, and the server is malicious. And according to the DDH assumption, which is implied by the DSDS assumption we have seen before, this value, g to the x1, x2, looks random. And so if you look carefully at the alpha value, this means that the alpha value also looks random. So we can just replace it by a random value. And then, using the DSDS assumption, we show that the resulting key depends, looks random if the server used a password PW prime, which is not equal to the password used by the client. But since the password of the client appears nowhere in the flow sent to the server has no idea of what password the client used, and he may only guess, and if he guessed incorrectly, this means that the key will look random, and that intuitively means that the scheme is secure. So basically, the server can only guess the password, and if he if he did not guess correctly, he will not be able to know the secret key used by the client. Okay. But that's, this intuition is a bit misleading because the PAKE protocol the JPEG protocol contains some important details which are labels. So labels are metadata of the proofs done by the client and the server. And actually, the security of the JPEG protocol depends on the choice of the label. So as we have already seen, if the label are the one proposed by, in the original paper by Howe and Ryan, so namely, if the label used by the client are his identity or his IP address, if you want, and if the label used by the server as his identity B or his IP address, whatever, then the protocol is secure, but the proof is very hard and the reduction is loose. Well, that's not so good. Worse than that, if you take the label chosen by the OpenSSL implementation, so which are, for the client, this is a bitstring client, not the IP address, but the bitstring client. And for the servers, this is a bitstring server. Then we show that the JPEG protocol is only secure when there is only one server. If there is more than one server, this is no more secure. And finally, if you use labels which are more commonly used in the cryptography community, so namely the label contains all the previous transcripts seen by the two parties, then we can show that the protocol is secure, obviously, but the proof is easier and the reduction tighter. So that's definitely what you should use. Okay. So, but first, what's exactly this simulation extractability property? So I've already slightly talked about that, but let's look at a clear definition. So the simulation extractability is a very strong property on the zero-knowledge proof, which basically says that if you have a valid proof, you can extract a witness from it, even if you are also simulating or faking proof in the same time. And so that's a very strong notion. And in PKC 2015, it was shown that the Schnorr proofs used in the JPEG are not simulation extractable in the random oracle model. I mean, you cannot prove they are. But assuming algebraic adversary, so this means slightly restricted adversary, which are still reasonable in practice, we can show that they are. And the proof is interesting from my point of view, and it's not as easy as you may think. So I encourage you to look at the paper if you are interested in that. Okay. So back to this label problem. So why is this bad to use these labels? So if you look carefully at the protocol, the labels are the only part where you can potentially identify the security, I mean the identity of the two users. So there is no other place where the identity of the two users appears in a secure manner. And so that means that if you use for the label of the client just the same bit string, and for the label of the server always the same bit string, you will have a problem. So more precisely, let's suppose that Alice has two bank accounts, a blue one and a red one. And she uses the same password for the two bank accounts. So that's really bad, but a lot of people do that, so that's possible. And an adversary can just forward all the flow intended to the blue bank account to the flow to the red bank account. And then Alice will think she's talking to the blue bank, but actually she's talking to the red bank. Okay, that may not appear a really big problem, but let's replace the blue bank by a test server, the red bank by a production server, and let's suppose that Alice wants to reset the test server. The adversary does this forwarding, rerouting of flows, and at the end, when Alice sends the command to erase everything on the test server, she ends up erasing everything on the production server. And so she gets fired. So concretely, it's not a good idea to use JPEG in that case. Or to use the same password or two servers, so it's not a good idea anyway. But, okay, but labels are, so we have seen that labels are very useful to identify users, and they are actually also useful to prevent mixing flows. So if each label here contains all the previous transcript, the adversary won't be able to mix flow, and that will make actually the proof easier and the reduction tighter. And actually, in some cases, it's not the case in the JPEG, but in some cases, you really need these labels, otherwise the proof does not work at all. But in the JPEG protocol, we are lucky with this minimal label, you can still prove. But that's difficult. OK, so with that, I want to conclude. Any question? Thank you very much.
We have time for 1 or 2 questions.
Can you say exactly what are algebraic adversaries?
So algebraic adversaries are basically adversaries who can do whatever they want, except on group elements. And when it comes to groups element, the only thing they can do is do the group multiplication or group division. They cannot do fancy things such as looking at the second bit of the group element and base their decision about this bit of the group element.
Okay.
Yeah.
So on slide 13, the redirection attack you are mentioning here. So how would the adversary implement this attack?
Oh yeah, it needs to control the network, but it's possible if you are connected on a free Wi-Fi or, for example.
All right. Okay. Thank you.
Yeah, good question.
OK, if there's no more questions, let's thank Fabrice.